Another mathematical model that uses exponential functions in it is something called learning curves. And these describe, among other things, product demand, Newton's law of cooling, certain types of learning procedures. And this model is of the form Q of t, quantity at time t, is c minus e to the minus kt, where c, a, and k are all positive constants. Here's an example. Q of t equals 50 minus 3e to the minus 5t. This happens to describe how many units of a product an employee can assemble after they've been working at the job for t days. So that's why this is called a learning curve. As you learn, you get better. We're not asked to find any of the constants here. We're just given them and asked to find some quantities. So let's find Q of 0. We're just going to plug in 50 minus 30 e to the minus 0.5 times 0. So we have 50 minus 30 e to the 0, and remember anything to the 0 power is 1, so we get 20. In other words, the first day an employee is learning to assemble this product, they can assemble 20. What's Q of 1? Well, let's see. 50 minus 30 e to the minus 0.5 times 1 is, this is the same thing as 50 minus 30 e to the minus 0.5. Now I'm going to rewrite this a little bit differently for reasons that will hopefully become clear later. Let's remind ourselves that having a negative exponent means that the thing really belongs in a denominator. So this is the same thing as 50 minus 30 over e to the 0.5 power. So we have 50 minus 30 over approximately 1.65. So that is 50 minus about 18.20. In other words, about 31.80. Let's try Q of 2. So that's 50 minus 30 e to the minus 0.5 times 2. And 0.5 times 2 is 1. So we have 50 minus 30 e to the negative 1. And again, I'm going to rewrite that as 50 minus 30 over e to the first power. So we have 50 minus 30 over about 2.72. In other words, 50 minus about 11.04, and that would be about 38.96 units that the employee could assemble. So they're getting faster, right? They can assemble more. First they assembled only 20, then 31.8, then 38.96. Let's look at Q of 6 now. Now we have 50 minus 30 e to the minus 0.5 times 6. Now 0.5 times 6 is half of 6, so that's 3. So we have 50 minus 30 e to the negative 3, which is the same thing as 50 minus 30 over e cubed. So we have 50 minus 30 over, and e cubed is about 20.09. So we have 50 minus 1.49. In other words, about 48.51. We're asked one more thing. What is Q of t for very large values of t? In other words, as time goes on and the employee gets more and more experienced at assembling these things, what's going to happen to the quantity they can assemble? So for large t, large time values, what happens to Q of t? How are we supposed to know that? Well, there's a pattern we can look at here, and this is why I wanted to kind of rewrite things. Every time we raise the t value, notice that the denominator of the thing we're subtracting gets larger. So first the denominator was 1.65. For Q of t, the denominator was 2.72. For Q of 6, the denominator was 20.09. So the denominator is getting larger. Now, what happens to a fraction if you give it a larger denominator? Like compare 1/2 to 1/3. Which is bigger? The 1/2 is bigger than 1/3. So as the denominator gets bigger, the fraction gets smaller. And we can see that if we look at what we're subtracting after I've done it on the calculator. First, we're subtracting about 18. Then we're only subtracting about 11. For Q sub 6, we're only subtracting about 1.5. So that as the t gets bigger, that denominator gets bigger, which means the thing we're subtracting is getting smaller. And what's going to happen as t gets larger and larger, Q of t will look like 50 minus 30 over super large denominator, which means we're going to have 50 minus a very small number. And so as you're subtracting less and less and less from 50, the values will actually approach 50. So we would expect that eventually an employee could assemble approximately 50 units of the product.